Now we're looking at the motion of a ball under gravity. We can see air resistance is significant here because it's not falling with a constant acceleration, but the velocity is increasing to a limit. Now, how could we use the graph to determine distance fallen? Well, we should know that the area under a speed-time graph gives us distance. So, simple answer to that question. Now, we want to show the forces on the ball at 2 seconds. So, let's go and see what's happening at 2 seconds. At 2 seconds, we can see it's still accelerating because the velocity is still going up. However, the rate of change of velocity is not as fast as it was at the very beginning. The gradient has decreased. So there must be some resistive force that's acting against the weight. So how do we draw that? Well, we draw one force to represent the weight. Let's call that the weight. Remember, we don't call it gravity, we call it the weight. mg, and there must be an upwards force that's less than the weight, so we need to draw a shorter arrow, and that's air resistance. Now, we need to use the graph to show that the acceleration at 2 seconds is a certain value. So, going back to the graph, the acceleration at a point is the gradient of a tangent to the curve at that point. So I'm going to draw in a tangent. To draw a tangent, normally you place your ruler against the curve so that it doesn't cross the curve, just touches it at that point. And you need to do it quite accurately to get a reasonably good value. That's close enough for me. So to find the gradient of the tangent, then we need to draw a triangle, and the larger you draw your triangle, the better. General rule is make sure your triangle is at least half the length of the line. So I'm going to draw it up to 4 seconds. So reading off the values here, the x value is changing from 0 to 4, and the y value is changing from 5 up to this value here, which is about 23.5. So the acceleration is the change in speed over the change in time. Change in speed was 23.5 minus 5 over 4 minus 0. Which to two significant figures is 4.6 meters per second squared. Maybe my gradient was not drawn very accurately, my tangent was not drawn very accurately, but it is approximately 4 meters per second squared. The mark scheme, by the way, allows a slope within the range 3.6 to 4.4. So you can see here, you need to have drawn this tangent more accurately than I did. Now to find the magnitude of the air resistance at 2 seconds, well, let's write down Newton's second law, because it's the total force that's giving it the acceleration we just calculated. So Newton's second law says that the total force, the resultant force, is equal to ma. Now the resultant force comes from two things. It comes from the weight acting downwards and the air resistance acting upwards. So mg minus, let's call it r, must equal MA. And to find the air resistance, we just rearrange this for R. Put the numbers in, the mass of the ball, the question tells us somewhere is 0.5 kilograms. G is 9.81, and the acceleration, let's use the 4 meter per second value that was stated in the previous question. That gives us approximately, to one significant figure, gives us 3 newtons. Now, we need to think about whether the air resistance at 5 seconds is, or how the air resistance at 5 seconds compares to the air resistance at 2 seconds. We're going back to the graph. We can see at 5 seconds what's happened. The gradient has decreased, so the acceleration must have decreased. For the acceleration to decrease, well, the air resistance must be greater, and that makes sense because the ball will be falling faster here, and at a higher speed it's going to experience more drag. So the mark scheme expects either one of those answers. First, that the acceleration is decreasing, from which we can see from the graph, therefore the resistance is greater. Or in terms of the fact that it's going faster, so the resistance must be greater. Now, for part C, we want to find the change in energy as the ball falls. So, change in energy is going to be the change in its kinetic energy plus the change in its potential energy. And let's take a change in energy to be an increase in energy to be positive. So we're actually trying to show a negative number, that the energy has decreased. Now the change in kinetic energy, if we look at the graph, the speed is going from 0 to 25 meters per second. So the change in energy is just a half v squared, where v is 25 meters per second, plus the change in potential energy. But the change in potential energy is a decrease in potential energy because it's falling, so that's minus mgh. So put in the numbers, half 0.5, 25 squared, minus 0.5, 1.81, 190, and the answer turns out to be approximately 780 joules. Now we have to estimate the increase in temperature of the ball. Now, why would the ball heat up? Well, this loss of energy must go somewhere, and it's gone into doing work against the air. But where's that energy actually gone? It's going to go into thermal energy, both of the air and of the ball. I would expect more of that energy went into the energy of the air, but to do this question, let's just assume, to begin with, that all of that energy goes into heating up the ball. So the energy we need to heat something up is Q equals mc delta T. And rearrange that, delta T is Q over mc. So the amount of energy we have available is 780 joules. M is 0.5, and the specific heat capacity of the ball is 480 joules per kilogram per Kelvin. So that gives us an increase in temperature of about 3 Kelvin. And of course that's just an estimate because we're assuming all of the energy goes into heating the ball. So that's what we need to say. Now part 2, What's binding energy? Well, binding energy of a nucleus is the energy that's released when the nucleus is formed from all of its constituent nucleons. And an alternative way of saying that, as the Mark scheme says, is the energy required to separate the nucleons from the nucleus. Now we need to deduce the binding energy of a particular isotope. So to deduce that binding energy, we need to find the energy that's lost when this nucleus is formed. And that energy loss is apparent because there will be a mass defect. This mass, or this rest mass energy, this mass energy of the nucleus will be less than the mass energy of the constituent nucleons. So what we want to find first is the mass defect. That's going to be equal to the mass of the constituent nucleons minus the mass of plutonium-239. So to work out the mass of the constituent nucleons, we need to work out what we have in this nucleus. Now we can see in the atomic number that there are 94 protons. So 94 times the mass of the proton. How many neutrons are there? Well, the mass number, the nucleon number, is 239. So the number of neutrons is going to be 239 minus 94, which is 145. So we need 94 protons, 145 neutrons to make this nucleus. The binding energy is going to be the mass of those separate, the mass defect is going to be the mass of those separate nucleons minus the mass of plutonium-239. Now we can find the mass of the proton and the mass of the neutron in the data booklet. We'll use U, the atomic mass number, atomic mass unit, for this calculation. That's going to be 94 times 1.007276. We need a lot of significant figures here because the difference might be quite small. And that difference comes to 1.95 U, which we then need to convert to mega electron volts. That's 1816 mega electron volts. But we don't want the binding energy of the entire nucleus, we want the binding energy per nucleon. So the binding energy per nucleon is going to be 1816 divided by the number of nucleons, which is 239, which comes out at 7.6 mega electron volts. Now here's a graph of the variation of binding energy per nucleon with nucleon number. And we have an equation here showing the fission of plutonium-239. So first, how many neutrons are produced? Well, to work out how many neutrons are produced, we need to balance the mass numbers in this equation. So on the left-hand side we have 239 plus 1, that's 240. And on the right-hand side we have 91 plus 146 plus x times 1. Now, 91 plus 146 is 2, 4, 2, 3, 7 plus x times 1. So x must be 3. And then we want to use the graph to estimate the energy released in this reaction. So using the graph, we need to find where, firstly the plutonium and then the products lie. So the plutonium has a nucleon number of 239, so the plutonium is here. The SR, the strontium 91, is here, and the barium 146 is around here. So the energy released in this reaction, well, 91 of the nucleons that have this binding energy form the strontium, and the energy they release is this difference here, the difference between plutonium and the strontium. So that difference is between, that's from 7.6 mega electron volts to 8.6 mega electron volts. So there's a difference there of 1 mega electron volts, and there are 91 nucleons that are releasing 1 mega electron volt. Plus the 146, sorry, that was 91. The 146, that release this amount of energy. So that's from 7.6 up to 8.3. So that's a difference of 7 mega electron volts. Sorry, 0.7. And that comes to $193, or approximately 190, because this is only an estimate, mega electron volts. Now, it tells us that stable nuclei with larger mass numbers have more neutrons than protons, and why is this? Referring to the properties of the nuclear force and the electrostatic force. Well, what can we say about the nuclear force? The nuclear force firstly keeps the nucleus together because it's attractive. And the nuclear force acts between all nucleons, both protons and neutrons. Now, what can we say about the electrostatic force? Well, in the nucleus, it only acts between the protons, and because the protons are all the same charge, it is repulsive. So that's trying to push the atom apart. So what do we have in larger atoms? In larger atoms we have more protons. So as we have more protons, that means the electrostatic force is more repulsive. And so we need something to balance it. We need a greater nuclear force to balance it. Now, how do we get a greater nuclear force? Well, the nuclear force is between all nucleons. The only way to get a greater nuclear force without increasing the repulsion is to add more neutrons. And the Mark scheme answer says something like that.